it was the year 1973, and I got a scholarship from Lebanon to study at Imperial College. So I went, and a week after I started, I was passing through the corridor. At that time, I really knew absolutely nothing about research, zero. I saw the name Salam, and to me, it's an Arabic name. The Prime Minister of Lebanon was called also Salam. So I knocked at his door. It was half open, and then introduced myself. Asked him, "Are you Lebanese?" He said. Yeah. Okay. So he said no, and then he explained to me that he's from Pakistan, and then he asked me, "Why? Do you want to study theoretical physics?" I said yes, because I love mathematics. And then he told me, "You are in the wrong department." So. However, a year later, having passed courses, I asked him to take me as a student. He accepted, and then he gave me two papers. One was June 1974, and then he has two important works, as we have discovered. One was the supersymmetry with Strasdy, and the other was with Patty. And he told me, read both and tell me which field you would like to go into. And being lazy, I adopted supersymmetry because it's new, few references. While the other, you have to really learn a lot. And anyway, it's as I'm going to show, Salam somehow was blessed. I think, as Mike Duff would call it, he was a magician. And because 40 years later, I would come back and would see this Patty Salam model coming out of nowhere in a unique way. So somehow, he knew something. And I think I got him a plaque, and this plaque, he kept it in his office. And it's in Arabic. It's, I think, it's a verse from the Quran, which really translates, "We opened for thee a manifest victory." And it was really in his office. Only people who knew Arabic would know what does it mean. But to me, it always rang true that, he was blessed and path in front of him was open. Anyway, so I will start actually today. So essentially, this work I've done actually with collaboration with Alan Kohn. It started in non-commutative geometry, which I have been working now for really many, many, many years. And we have been joined by Slava Mukhanov on this project. And the main idea in this is, suppose that at extremely high energies, that the volume of space-time is quantized. Then what would it mean? It would mean actually that the volume, which of course the present volume of the universe now is 10 to the 60 Planckian units, it must be integer multiple of these units. I would really work in Euclidean space, so of course I would not really answer the question of how to go to Minkowski here. We have an answer, but I will not have time to go through it. So the basic idea is the following. You consider a mapping from a manifold to a force sphere. So this is the usual map. And this map has a degree. It's known that such maps from manifolds to spheres have a degree. And so essentially, this is the four form. dy, 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 dy is a four form. And then if we equate this with the volume 4 of the manifold, then you'll be guaranteed that when you integrate this volume form, you would really get actually the winding number over the sphere. And that number is known to be an integer. So that actually would immediately guarantee for you that the volume of your space is an integer. However, this has consequences. And the consequence, which somehow is not desirable, is that once you equate the volume form to the degree map, then the Jacobian of the transformation is non-singular, which means you can really have the inverse map is non-singular, which means that the topology of the manifold, for this to hold, must be a sphere, must be that of a sphere, not necessarily a sphere, the topology of a sphere, and which means that our space-time, the way it would be, it would split into disconnected pieces of bubbles. So you'd really get the bubble picture. Of course, one can really argue that if I have bubble picture, I can condensate them. But anyway, we'll not go through that route. We'll try something else. And what we do is the following. I would rewrite what I have done now by using Clifford algebras. And so the map Y, we associated it with a Clifford algebra. Remember, it's for a 4-sphere. So Y will be YA gamma A, and then you have really 5 gamma matrices. In addition, we introduced the Dirac operator over the manifold, and it is known, if you look at here, it has a spin connection, and it has, the Vierbein or the inverse Vierbein. And then the previous condition that I have written about the volume form can be summarized in a very compact way, in which we say that the expectation value, which means really the trace over this gamma matrices, y dy to the 4 is a gamma, where gamma is the chirality operator over the manifold. Now, if you look at this relation, it really looks like it's some form of Heisenberg relation. Why? Because everything is slashed now. Remember, Dirac operator is slashed with a gamma, so it's a d. And of course, in momentum space, is nothing but the momenta. It's p slash. So this is p slash, and the y is like coordinates, because after all, when we map a manifold to a sphere, the independent y's will be to zeros approximation will be the coordinates themselves. So it looks like px is 1. It looks. So it's some form actually, but of course actually we know that it's really a Heisenberg relation in the phase space which we created from the Dirac operator and the coordinates of the mapping. Okay. So here I'm repeating the argument that this is really a bubble picture and we have to modify it slightly. So what do we do? We notice actually when I consider the Clifford algebra, gamma gamma, there is really always a sign ambiguity. And I can consider to be plus or minus depending on which Clifford algebra I take. And then the calculation doesn't change at all. Nothing changes in that. And still, but the only thing actually instead of gamma, I would get kappa gamma. And you already have 2 possibilities, and you can consider them to be like 2 spheres. Now, this, having worked in non-commutative geometry for a long time, we know actually that this is nothing but the Chern character for non-commutative spaces, which is a special case of the orientability condition in non-commutative geometry. So anyway, so what I'm going to do actually, I'm really going to take this relation, try to embed it into this non-commutative framework, and we'll see actually what does it give. Okay? The first actually, non-commutative space, or this new geometry, which was redeveloped by Alan Kohn since a long time, is a new way of doing geometry. It includes Riemannian geometry, but also it includes spaces which are discrete, spaces which have continuous dimensions or Hausdorff dimensions. It's really a more general setting. And this more general setting is really based on defining spectral data. And this spectral data has a triplet: algebra, Hilbert space, Dirac operator. And in addition, for even dimensional spaces, you'll also have the chirality and a reality operator, which is very similar to charge conjugation operator. So what's A? Is an associative algebra with involution and unit element. H is a Hilbert space. And D is a self-adjoint operator on H with bounded spectrum for D squared plus 1 inverse. Anyway, if you are not mathematically oriented, you don't need to worry so much about it. It's just data, okay? And one can reconstruct the geometry, and in a way, one can, as I said, we need also the chirality operator and the reality operator, and I will tell you what these things are. These actually, they must satisfy certain properties, that the square of j squared is plus or minus 1, j with d is it either commutes or anti-commutes. Similarly for j with the gamma, and epsilon prime can take only the value minus 1 and 1, which tells me that all these spaces that I have already defined will be defined modulo 8. It's really very similar to people familiar with supersymmetry. It's exactly the same phenomena. And that's actually, in the mathematics they call this the K-O dimension. The K has to do with the K theory and the orthogonal, something that Atiyah did some years ago. Anyway, so let's actually make contact at least for Riemannian geometry. What do you have? For Riemannian geometry, we now have the algebra is C infinity of M. It's the algebra of of differentiable functions. H is L squared of S. It's the usual Hilbert space. D is the Dirac operator, which I have already written, and chirality, and the J is the charge conjugation operator. Now, what this J does actually, it really sends the algebra, it's commutant, and so I can define through the J B star J inverse, and this actually commutes with the A. What does it mean actually? When you are acting with the Hilbert space, you can act on the left or on the right, and somehow J would change a left action into a right action. So in other words, actually now, I go back to my quantization condition, and remember I started with Y, but because I have the J, this tells me that I need a Y prime. And this J actually sends the Y with the Y prime, where Y and Y prime now commute with each other, which means I need two Clifford algebras and not one Clifford algebra. And remember actually that the sign ambiguity that we have, I really have to consider them. I consider both of them, but one has to do it in a simultaneous way. You cannot take this and that. So how to do that? You introduce something called idempotent element, with the property that E squared is E, and E, of course, is 2y minus 1, because E squared, as you see, you can immediately verify that E squared is 4y squared, which happens to be 4 minus y, and then the cross term, they cancel, and then you are left with that E squared is E. And similarly, I can take E prime to be 2y prime minus 1, and then I define an object which Z is 2E prime minus 1, such that Z squared is 1. And now my relation, I only have one relation, but for both Clifford algebra, would tell me that Z dz to the 4 is gamma. Now, this looks innocent, but this now has grave consequences. Let's see why. First of all, only actually in 2 dimensions. See, I have written in 4 dimensions. There is another relation I could have written also in 2 dimensions. And then only in 2 and 4, this relation would split into 2 pieces, actually. Here. It would split into the y piece, y prime piece, no mixing terms. If you try to do it, say, in 6 dimensions, it doesn't work. If you try to do it in, 3 is different. It's odd dimension, so you have to do something else in that case. But there is really deep reasons, actually, why this relation only works in 4 dimensions. And now, what does it mean? It means, let me look at the Clifford algebras. One thing I did not tell you is that when I take the Clifford algebra of the plus with 5 pluses, is known that it is nothing but, it's really 4 by 4 matrices, but it is the M2 of H. It's the quaternionic matrices. I learned it from Bob's course at Imperial College. So this is M2 of H, so it's C plus is M2 of H plus M2 of H, and with the minuses, it happens to be M4 of C. So you really have 4 by 4 matrices, 4 by 4 matrices. And it means actually, in this non-commutative jargon, the algebra of my finite space, which I'm really putting on top of the manifold, happens to be given by M2 of H plus M4 of C. And out of that, now we really can tensor this algebra. It's a, it's really when you say non-commutative here, is really non-commutativity is really trivial in the sense that they are matrices, they don't commute with each other, and this is why they are really non-commutative. But on top of it, you really have to tensor actually the two spaces together, and tensoring is really non-trivial. Of course, actually, this part is trivial, that the algebra is C infinity of M cross, this is cross, this is cross. What's non-trivial is the mixing between the Dirac operator. The Dirac operator mixes the two, discrete and continuous spaces in a non-trivial way. And I will show you actually what are the consequences of this. The consequences are really great. Now, first of all, I have this now. I have to take this into account. And this is my Dirac operator. And as I said now, let me go back to my relation. And now actually what I'm telling you is that the volume form on the manifold M is this degree of the y plus degree of y prime times the volume of S4. Now actually if I try to use the argument I used before, that now I have actually that the inverse of the Jacobian of the pullbacks, I have two pullbacks now, the sum is non-vanishing. But each could vanish. So one has to do, actually, you have to study the kernel of this inverse map. And then you have to show that this is always possible for an arbitrary manifold. However, actually, what we really find that it is possible to define this inverse map such that the volume is the sum for only spin manifolds. There is an abstraction which has really related to the Stiefel-Whitney class, but the proof actually is really difficult. And of course, actually, we are humble physicists, and except for Alan Kohn, who is a master mathematician. So of course, he supplied the proof, but it took him, some doing, And it took some correspondence with Donaldson, because the Donaldson is the experience about 4-dimensional manifold. As I said, this only works for 4 dimensions, and the reason is that the inverse of the map would have a surface of codimension 2. It's really very tricky in this case. It's really a critical case. Anyway, the proof does work. And then actually, what does it mean actually when I say it works? It means that the 4-dimensional manifolds emerges at the inverse maps of the product of the two spheres of Planck size. It means you really need two quanta. Remember, these two spheres would correspond to two different Clifford algebras. They're not completely identical. And then it means their inverse map. So of course you are taking a sphere, you are pulling it back, and the shape is not a sphere. The shape, and it's really a mixture of the two. It cannot be only one, because the one could vanish, would have a kernel, and the other one will come to compensate. So you have to really mix these two, the inverse of the two quanta, in such a way that you reconstruct your manifold in a way that the volume of this manifold will be an integer number. So now actually, all of this, as I said, we have the manifold, we have the Clifford algebras, and which defines for me this unified space, and I have to take it into consideration. And notice actually now the numbers 4 is everywhere, because the manifold has dimension 4. I have two Clifford algebra, each is 4 by 4 matrices. So we have 4, 4, 4. You have 3 4s actually coming there. And now actually let's work out the property of this space. First of all, I consider an element of the Hilbert space, which, they are really usual spinors, times HF, and this is HF in the algebras. Remember, I have two algebras. And should satisfy, it so happened actually that also for this algebra, you can define both actually conditions, which is the reality condition and chirality condition simultaneously, because this is, this space would, in its Lorentzian version, would have dimension 10, essentially. because the internal space, which I have described with the two algebras, really have dimension 6. So it looks like, a Kaluza-Klein theory, but not Kaluza-Klein theory, because we're talking about finite spaces. I'm not talking about infinite spaces. And this, this algebra, this operator here, what does it do? It exchanges the two algebras with each other. It sends actually the M2 of H to M4 of C. It interchanges them. So as I said, this is only possible for KO dimension 6, which happens to be the case. So we have, really everything works. And then if I look at the representation of these fermions, what do I really have? I have a 4 of space-time, a 4 with respect to the first M2 of H, and a 4 with respect to M4 of C. And of course, in a space-time spinner, forget about this alpha hat. You have only, it's a 4-4 representation. What's a 4-4 representation? It's 4-4 representation is a 16 spinner. 16 spinner, it's exactly the same guy that Patty and Salam wrote for their Patty-Salam models. We are going to show it's exactly the same. Everything comes out to be the same. Okay, so now in addition, actually, I'm not done because I have to put a chirality condition on this space. And the chirality condition on this space, what does it do? This gamma. Remember, before I told you that here. You see here, this gamma and J, and the gamma and the gamma should commute to the elements of the algebra. Probably did I write? Probably didn't write it. Okay. So this gamma should commute to the elements of the algebra. And what does it do actually? This gamma breaks this algebra M2 of H into H and H. What is this H? It's H right and H left. And I will show that each H later will give me an SU2 in this. We'll see how. Anyway, so we start actually decomposing. And what do we really get? We get actually that immediately we start writing, you get a new R, ER, L, and U, D, Q. And now actually we see actually that the lepton is the fourth color. And actually that's the thing I didn't like when Salam gave me this paper, because I remember they called the fourth color lilac. I didn't know this lilac, So, and this L is lilac is for the lepton number. So then, now I realize what they were talking about. 40 years later. So. All right, so essentially, these spinners are, representations of SU2 cross SU2 left cross SU4. And now, but we are not done because, I have introduced this algebra, and I have some Dirac operator, but this Dirac operator is not invariant under automorphism because, remember, an element of the Hilbert space can transform under some unitary transformation of this algebra. And psi is U phi, where U is U hat, and so on. And so how can I repair this? I can repair this easily, exactly like what we do in electrodynamics by adding some connection to the D. And this connection, you say it's D plus A. And then you can compute what this D plus A, and the A happens to be given by this expression. If you look at this expression, then you discover that A has A1 plus GA1 J inverse plus A2, where A1 is this and A2 is this. It's something you compute because it's not that difficult after all. They are just simply, functions, values on matrices. So we are doing matrix algebra, no more, no less. Actually now, we can do it with Mathematica. After we do everything, we just write, few lines, and it gives you the answer. So, but everything was done first, of course, by hand. Now here actually is the crunch. We really have, I noticed that this, what I called A2, could vanish if one condition is satisfied. And if this condition is satisfied, it doesn't actually, then I have really separation between the algebra and its opposite with the U hat. So if I put this condition, A dB hat, then the standard model will come out as a unique solution. We'll show this. And if it's not satisfied, then I will show that you have only the full-fledged Patty-Salam model. We really have two cases, two unique cases. One in which you have a simple connection where the algebra and its opposite do not mix, and the other where they do mix. In this case, I have to take the Patty-Salam model. So there are only two solutions, actually. Both which Salam anticipated many, many years ago. Okay, so now actually how to proceed? To proceed is very easy because now we have to compute actually this connection A. And the connection A, the recipe I have given how to compute the connection A is simply taking commutator of matrices with the Dirac operator. And I give you an example. I really have it's a huge matrix because you are talking about 16, and then you have the conjugate space, that's 32, and then you have Clifford algebras, that's 96, and then of course then we have to add 3 generations, but that's we do by hand. 3 generations. Unfortunately, we have no explanation for the generations yet. Who knows? Maybe it will come out. Now, let me talk actually, in this case, if you do the Patti-Salam, unlike actually the usual Patti-Salam model, this one comes with a fixed Higgs structure. And we have only 3 possibilities for the Higgs structure, which I listed. But, there are three possible configurations for the Higgs structure. So I say 3 classes of Patti-Salam model. And I list actually the sigmas. They are not that strange, actually. They all appear in the Patti-Salam paper and later by Mohapatra paper. So they have been considered before exactly same configuration. But here they come with it. Anyway, here actually, unlike you don't need supersymmetry because we have shown that with this Higgs configuration, it is possible for the 3 couplings to meet at around 10 to the 16 GeV. It is possible. Let me come to the special case. So the special case actually is this, when this order 1 condition is satisfied, and then we really get many conditions and many consequences that it really reduces immediately to standard model as a unique solution. Plus, it's not only the standard model, of course, it's standard model plus right-handed neutrinos, because the right-handed neutrinos are part of the spinor. The spinor have not changed at all. And on top of it, actually, we really get a scalar field. The scalar field actually would play an important role because of the following. So, this scalar field, what does it do? It is a scalar field that gives Majorana masses to the right-handed neutrinos. In addition, there is a problem actually with standard model. And the problem with standard model that if you really run the normalization group equations, you'll discover that this value of lambda, the Higgs coupling, lambda h to the 4, really becomes negative at 10 to the 11. There's a known problem. You run, and then, so you really, of course, you cannot really run the standard model all the way to Planck. It will, However, once you put this field sigma, it really saves the situation because the running does change, and then you have really no problem. In addition, actually, here, unlike the usual standard model, because the gauge and it's very similar to supersymmetry, where the gauge and Higgs couplings are unified, they are related to each other actually, you'll discover actually the top quark mass is predicted to be around 170 GeV. So this actually is, so the standard model that we really get from this picture is, has some predictive power, not everything of course, but it has some predictive power. And of course, here there's a problem actually with the meeting of the coupling constant. They don't really meet at 10 to the 16. So maybe actually, you are going to get the picture which is standard model all the way up to, well, maybe up to 10 to the 11 or 10 to the 12, where actually then this Patti-Salam models would start to come in. And so you are really going to get a picture which is rich in such a way that a standard model will keep holding. So if nothing is observed, this is perfect explanation why nothing has been seen or will be seen. Yeah, and the other possibility, as I said, would be the Patti-Salam models, whether they would have low energy consequences or not. There are many possible scenarios, and then, it's not that easy to say. Now, the Fermi action is always given by J psi, dA psi. And what about the Bosonic action, actually? Now, the nice thing about non-commutative geometry is the following. It's really spectral theory. You are really building your manifolds out of the spectrum. And, there's a famous problem in mathematics, which due to Marquardt, in which he posed the question, can we hear the spectrum? Can we hear the shape of the drum? And so the shape of the drum, you'll discover that, of course, it was proven that you cannot, because there are counterexamples, and the counterexample has to do with, there are isospectral manifolds. Manifolds, exactly the same spectrum of the Laplacian. However, this, if we take the Dirac operator with this data, it's uniquely defined. So in this case, you can hear, as I would say, the sound of the shape of a supersymmetric drum, in which, or a spin, where a spin manifold can be defined. If you can define a Dirac operator with this algebra, then I think okay. So now, what do we do? So the idea is the following. You have a Dirac operator. You look at the eigenvalue problem. You can find the eigenvalues. And then, of course, actually, what's really remarkable is that the eigenvalues are all geometric invariants. Eigenvalues of the Dirac operator are geometric invariants. So you really can, by looking at the spectrum, rederive or rediscover the geometry. So what we do, instead of writing things, you take an arbitrary function of f of d over lambda. Because remember, d has dimension 1, and therefore lambda is a cutoff scale, which can go all the way up to the Planck, or a little bit below the Planck. And if you take trace of an arbitrary function, positive function, of d over lambda, then it really amounts to counting the spectra below a certain scale. And this actually should really give me the bosonic action. It looks innocent, but in reality, actually, what one can do, you can take this function f, you can expand it in a power series. It will become functions of powers of d. For powers of d, you can use the gamma function representation, change it into exponential through a Mellin transform, and then it's just nothing but a heat kernel expansion. So as long as you are doing your calculation at scales below lambda, you can use the heat kernel expansion to compute this guy. And what does it give, actually? It gives me, the full answer. For example, what happened here? This is just a calculation. You just calculate with all these matrices I told you about. This is only for the special case of the standard model. Patty Salam we have already also done. Not much different, except, that the Higgses are a little bit larger. But note here, this sigma field that I told you about, because they couple to the Higgs h bar h, and they have kinetic term, they really change the RG equation and save the standard model, and the standard model could run all the way actually easily up to the 11th and the 12th, no problem whatsoever. Okay? Problem will come at 10 to the 14, because then the coupling constants which are supposed to meet, they don't meet completely. And you need new ingredients, which so you see actually here, you get the cosmological term. Now actually here the important point, now actually we have already quantized the volume. So it means that root g here, the integral of this quantized. Now the question whether is it renormalized or not? Because now it's an integer. If you realize something which is an integer, in Euclidean space, it would not budge. But in Minkowski, then of course there is no. In this case, you have a topological number. So actually, that would be an interesting question to answer what really happens there. And notice actually that here you get, besides, these are the Yang-Mills fields. Here you get the Gauss-Bonnet. Here you get Weil square. And you get all these conformal couplings here, while here is not conformal. And now the beautiful thing is the following, you are really getting a mass term for the h bar h. So this actually, now you tell me actually in all this, where this h field came from. The h field in this case are nothing but the components of the connection along the discrete directions. So this is the way actually gauge fields and Higgs fields are unified with each other, because you have a discrete space. You can think of it actually as also, parallel space, because in this parallel space picture, then you are really going to get a connection between the two sheets, for example. And what's the distance between the two? The distance between the two would be 1 over the square of the scale, in this case, the Higgs mass. So the Higgs mass actually, so in other words, once you really climb to the Higgs mass, the two couples would start separating, and you would start actually see the difference. Of course, it's a bit more complicated than that, but at least this is an intuitive picture one can think about. Okay. So let me, summarize. We started with now, this is what actually a two-sided relation. Why it's two-sided? Because remember, we have y and y prime, and they are competing in order to satisfy this inverse map, so that you really get that the volume of your space is an integer multiple of the Planck units. Actually, one thing I didn't mention is that this number, in the proofs, we needed that this number should be larger than or equal to 5. In other words, our space should be more than 5 Planck units. Of course, now it's 10 to the 60, so I think we should not worry about it. But to start with, you need 5 units in order to start making geometry. In other words, we are really building the geometry not from charts like in the Riemannian manifold, but we are building it from the inverse map of the spheres. Because now actually I can even forget about the Riemannian geometry aspect, and I define actually my space through these relations. I can define my non-commutative space, and it doesn't really have to be a Riemannian. In this case, as you see, it's not a Riemannian manifold, it's really a non-commutative space. And then I can ask, what are the solutions of this equation? The solutions of this equation will define for me my space-time. So now actually we deduce that the non-commutative space is generated, which is a product of a continuous 4-dimensional manifold times a discrete space of the algebra M2 of H plus M over C, and would give rise to a unified model of all interactions with Salam symmetries. The standard model is a special case and is unique, including a singlet responsible for the Majorana masses for the right-handed neutrino. There are many, the thing one actually also, I forgot to mention here, the H bar H really comes with a minus sign. It's a beautiful thing. And of course, before I thought it's a miracle, but then, I discovered that it's simply because in the heat kernel expansion, you are expanding E minus TD squared. When you expand the minus, you get plus, minus, plus. So that actually really gives you this Mexican hat potential. And it explains why you have spontaneous symmetry breaking, why the symmetry of this SU3 cross SU2 cross U1 is breaking into SU3 cross U1. And you have a prediction why that there's only one Higgs doublet and not more than one Higgs doublet in this picture. So you see, it's a very concise picture, and it really only came from our starting point, which is this relation. And it's simply, you have to say the number 4. The number 4 will give you the representation with that you have a 16 spinner with a certain representation. There's no guesswork. Everything actually is unique. And probably I should finish by saying, I'm grateful to the wisdom of Salam for, guiding me all these years. Thank you.
So it's well known that if you want to have a unified model of all interactions with the Salam symmetries, you should have spin 10. Otherwise, the gauge couplings are not unified. So what happened to spin 10? Because you have a 16 spinner. Spin 10 we often call SO10, right?
Right, yeah.
So what happened to spin 10? Why didn't you see that in your description?
In the description, why do I need spin 10? Why SO10? Why do you need SO10?
Otherwise, it's not a unified model. Because there is, by unification, we mean one gauge coupling at a gut scale.
Yeah, yeah. Well, actually, you can have two here.
To get that, you have to have spin 10, or SO10 we call it sometimes. So it's really spin 10, right?
Well,
which has a 16 spinner.
First, actually, you have two couplings, not one.
You have, in principle, 3, But
No,
you could have left-right symmetry maybe.
Right, yeah. So it's essentially really two, because
So you
left
see-
and right should be
so
the same.
that's the
actually.
other thing. You had this conjugation symmetry you spoke about. Spin 10 already has that symmetry. It interchanges left-right.
Yeah.
But if you just stick with Party Salam, then you don't have that.
We did the calculation, and they do unify at not only this was repeated independently by a different group, and we see unification at almost 10 to the 16, little bit below 10 to the 16.
No, but what happened to spin 10? Why don't you see it in your construction?
Why should I
When
see
you have a
spin?
16 spinner,
No, but
that's
16,
naturally
sorry,
SO10.
it's not 16. It's a 4-4 spinner. By definition, remember, I have two algebras. I have M2 of H, M4 of C, and I have something that shifts one into the other. So M2 of H is a 4, M4 of C is a 4. It's 4 times 4. It doesn't come from the 10. It's not the 10 representation of SO10.
No, it's not 10. I mean, the 16 of SO10 gives you just 4 to 1 plus 4.
I'm
1.
not disputing that. That
Yeah.
SO10 can break and go through this phase, but it doesn't. We don't start from SO10. We are starting with the symmetry, which is smaller than SO10, and it's not. We are forced on it. This is the only thing we can have.
Oh, well, I think you should see SO10.
How?
Because you see, you have Party Salam, so you have charge quantization, right? Mm-hmm. So therefore, the monopole, if you compute the monopole charge,
Yes.
it is 2 units of Dirac charge,
Yeah.
right? So you should also see in your theory a particle which carries half a unit of electric charge with no color, but you don't have that.
Yeah, I don't.
And in SO10 we can understand it.
Are you
see?
telling me that all the Party Salam models are wrong if they don't go to
No,
SO10?
of course not. They are perfectly right. I'm saying that you cannot claim that you have unified the theory without having an SO10.
Look, I unified. You know where I unified?
Of course they are right. Party
It is-
Salam is not wrong. Who's
It
saying
is.
that?
It is. This is a unification to me. Here, this equation. Okay.
Let's thank Ali again.
Okay. Thank you.